All right, we're going to just briefly touch on solid state. The book actually goes into more, but you only need to know as much as what's on this PowerPoint. So remember that a solid is a nearly incompressible state of matter. It has a well-defined shape, and so the units making up the solid are in close contact with each other, and they're in fixed positions. But I wanted to talk about the different types of forces holding them together, and we have to include, so we still have the same ones that we talked about, dipole, hydrogen bonding, and London dispersion, but we have a few others as well. So that would include ionic and a few others. So solids are characterized by the kind of force holding the structure together, and sometimes they're intermolecular, like I said, dipole, hydrogen bonding, London dispersion, but in other cases there are some chemical bonds holding them together. So like I said, ionic, there are metallic solids, and there are also covalent solids, which are the strongest. So there are 4 types of solids. Molecular, and these are the ones that we've already been talking about in terms of liquids and gases. So those only have intermolecular attractions. So those are there's the normal things we've been talking about. We also have metallic solids that consist of a metallic bond. We have ionic compounds, so obviously that's an ionic bond, which is a chemical bond, not just an intermolecular attraction. And then we have the covalent bond. So let me talk about each of those. So a molecular solid is just a solid that consists of atoms or molecules held together by these intermolecular forces. So that's what, like I said, we've been talking about already. So like water, carbon dioxide, neon, dry ice, any of these solids, solid ice, anything that's only held together by intermolecular attractions is considered a molecular solid. So there's our ice, which is water over here, solid hydrochloric acid, and solid dry ice. Everything's just held together by these intermolecular attractions. These tend to have the lowest melting points of most of all the solids. We'll talk about that in a minute. Metallic solids are solids that consist only of the metals, positive nuclei held together by a surrounding sea of electrons. So that's what a metallic bond is. So the positively charged atomic core are surrounded by the electrons that are kind of free to move, and that's why metals can conduct electricity usually and conduct heat as well. So any of our metals that are just metals like iron, copper, silver all have this kind of there's quite a wide variety, but you can see here's a bunch of positive nuclei surrounded by electrons, and the electrons are kind of in there, kind of surrounding them. So nuclei and then electrons surrounding them. Now an ionic solid, so these are all of our salts. Ionic solid is one that has positive ions and negative ions held together by an ionic bond. So these are full-blown charges that are opposite. So we have all of our salts that we talk about in first semester: cesium chloride, sodium chloride, zinc sulfide, lots of different. All of our salts are ionic solids. And so here's just some examples. So here's sodium chloride, just table salt. This is actually what table salt looks like under magnifying glass. So you can see that cubic shape there. Cesium chloride is also cubic, but it's a little bit different. You can see these are just alternating positive, negative. This one's got kind of a funky shape to it. Zinc sulfide has there's all kinds. You could take a whole class on just these different shapes and what they end up looking like. But mainly, you just want to know that they're solids that are ionic. And then finally, we have what's called a covalent network solid. These are atoms that are all held together in large networks just by covalent bonds. So not ionic, not intermolecular. And these are things like diamonds graphite, quartz, glass. They're just huge networks. So you can see here, here's quartz. It's just a bunch of silicon and oxygen bonded together. It just keeps going. Here's glass, which is also silicon and oxygen, but it's not as regular shaped as quartz is. Here's carbon all bonded together in a diamond. So it's got that tetrahedral shape just going on in infinity, and that's why diamonds tend to have that. You can have those sharp edges because you're just cutting a covalent bond. Graphite is actually a bunch of carbons stuck together as well, but they happen to be sort of in these sheets of carbon. So it's these hexagonal kind of carbons bonded together, that, and graphite, which is like lead, pencil lead, which is not lead, it's graphite, they kind of slide by each other, and obviously they're not nearly as hard as diamond, but clearly if you've got carbons under a lot of high pressure, eventually they get formed into a diamond. So these are covalent network solids, and they tend to have since they're very, very strong bonds, they're very, very high melting points and such. So we're going to go over that next. So molecular compounds are either atoms or molecules. They only are held together by intermolecular forces. Then we have our metals, which are the nuclei with the electrons surrounding it. Then we have our ionic and ionic bonding, and then we have our covalent network. And so we can look at different physical properties similar to what we did with liquids and gases. We can look at melting point. How is melting point affected by the structure of the molecule, by these attractions and types of bonds? We can also look at hardness and conductivity. So it's very similar to what we've been talking about with hydrogen bonding, and we're just adding a few more layers to it. So melting point and structure. For a solid to melt, we have to overcome the attractions between the units. So molecular solids, even hydrogen bonding, which is the strongest of the intermolecular attractions, they're still pretty weak on the scheme of things. They're much weaker than the covalent bonds. So molecular solids tend to have low melting points, below 300 degrees. Metals tend to have high melting points, but there's a whole lot of variability. It depends on what group the metals are in. Groups 1A and 2A are very low melting points, but then if you move into the transition metals, they tend to be much higher. There's so much variability that I can't ask you to compare those. So elements in the middle of the transition metals have the highest melting points. Ionic solids and covalent network solids because those are actually chemical bonds that have to be broken, they have very, very high melting points. So ionic solids can have quite a lot of variability. It will depend on the strength of the ionic bond. So for example, if the charge is higher, it should have a higher melting point. If the ions are smaller, that means that they're closer together, so it should have a higher melting point. So like for example, if you looked at, let's do this, NaCl versus MgS, since this is a +2 and a -2, it should have a higher melting point than this, which has a +1 and a -1. So there is some variability, and there is some ways to kind of interpolate it, but not too much. Smaller, so again, similar, so like NaCl should have a higher melting point than something like strontium iodide, which is wait, let's see, not strontium, let's try ribit or cesium, like cesium bromide. So these are much bigger molecules, and these are much smaller ions. So the closer they're able to get to each other, the harder it is to pull them apart. And so smaller ions tend to have a higher melting point than something bigger, and then the higher the charges should be. And again, there's some variability, but you can kind of see that. So if we kind of look at this, and again, we have to take it a little bit with a grain of salt, but here's all our molecular solids. So neon, which is only dispersion. Hydrogen sulfide is is a polar, and then we have our hydrogen bond. So you can see here, we can see how boiling point increases with increasing strengths, and also melting points also increase. But you can see on the scheme of things that all the melting points of our molecular solids are much, much lower than our metals and, well, not mercury, but our metals and our salts. So then our like I said, it's really hard to see there's quite a variety of melting points here for metals. You can see quite a range here. So in the middle of the transitions, the group 1A, mercury, which obviously is a metal, is a liquid at room temperature. So boiling point, of course, increases. And I couldn't ask you to compare those because you wouldn't be able to do that. But overall, metals are higher. In general, metals are higher than molecular. And then our ionic, again, tend to be much higher than there is some overlap, but in general, they tend to be much higher, of course, than molecular, and they tend to be a little bit higher than metal, depending on the metal. But what I want you to see here is, like I said, so cesium chloride, which are bigger molecules, is a little bit lower than sodium chloride, which is a little bit higher, which is still much lower than, because here these are both +1, -1. So size, as it gets smaller, it's higher, and then the increase in charge will increase and then here's our covalent compounds are very, very high. Some other things too, hardness and melting point kind of go hand in hand. So molecular solids tend to be rather soft. Covalent network solids tend to be very high and very strong and rigid. You know, think of the diamond, one of the strongest compounds on Earth. So diamond and silicon carbide are both three-dimensional network covalent compounds, and they're some of the hardest materials known. And our ice is obviously very, very soft in comparison. Molecular and ionic crystals tend to be very brittle. They fracture along crystal planes, where metallic solids are malleable because the electrons. And then again, molecular and ionic solids tend to be considered non-conductors. I know ionic, but if they're solid, only once they're melted can they conduct electricity. Ionic compounds will, once they're molten, are free to move, and then they will be conductors, but the solids themselves are not. And we know metals tend to be considered conductors because they have the electricity can flow because the electrons are free to move around. And so these are just some properties. I focus more on the liquids, but you should be able to do a little bit with the solids, kind of what I've talked about here. So molecular tend to have low melting points, tend to be soft and brittle and non-conducting. Metallic, of course, is variable, tend to be conducting. Ionic can be high melting point to very high. They tend to be hard and brittle. And covalent is very high and usually non-conducting. Just a few more things to tie up. Solids can be crystalline or amorphous. Crystalline solid is something that is very regular. Each crystal is well defined, ordered structure. It's three-dimensional, very ordered. So salts tend to be solids that are very regular, very crystalline. Sucrose, once it's in a solid, it's very regular. Whereas an amorphous solid is very disordered. It doesn't have well-defined arrangement of the units, and glass is considered amorphous. Right, so that is all of this chapter. What are some things you should be able to do? You want to know the phase transitions and describe a heating curve. You need to be able to calculate the heat required for a phase change if you're given the delta H for the phase change. Be able to understand how pressure and temperature are related to a phase, the phase of a compound on a phase diagram. Be able to describe the changes, identify and describe the intermolecular forces, determine the relative vapor pressure, boiling point, viscosities, depending on intermolecular attractions, kind of like those examples I did. Identify the types of solids, and again, be able to determine relative melting points, hardness, based on the type of solids. So that is this chapter.